Let's talk about what it means to collect like terms. So we have some examples here. We have pairs that are like terms. So we have 4x squared and 6x squared. Another example of terms that are like are negative 8x and 12x. We have some examples of pairs that are not like terms. 4x squared and 6x, 9x and 12. Okay, so we're kind of noticing something that the variable and the degree dictate whether or not terms are like. So, which of the following pairs are like terms? So I'm looking for whether or not they have the same variable and the same degree. So in this case, I have 5xy squared and 9xy squared. Well, they have the same variables and the same degree. So these are like terms. I then have 56 and 12. They don't have any variables. They're both constant terms. So these are like terms, meaning I can actually do the math there. And then my third example, I have 7xy, and then we can also write this as 1xy. They have the same variables and they have the same degrees. So these are like terms. If we look at 5xy squared, 5x squared, y squared, yes, they have the same variables, but the degree on x is different. So these are not like terms. 90 and 90x, well, one has a variable and one doesn't, which means one's a constant and one is a monomial. So these are not like terms. 7y squared and 3y, yes, it has the same variable. However, they do not have the same degree, which means they are not like terms. So in our own words, how can we identify like terms? Terms that have the same variable and degree. If you want to think of it a different way, that's totally cool. So if we go ahead and simplify, I have 5x minus 6y minus 2x plus 2y plus 1. Well, I like to go ahead and identify which variables are similar or which ones are like. Well, I have 5x and I have negative 2x, so I'm just going to write those over here. Any other x's? No. I have a negative 6y and a positive 2y. I'm going to write that here. Any other y's? No. And then I have one constant term and no other constant terms. So if I was to quickly just regroup that equation or that problem, I would get something like this. So it's a lot easier to see. I can take 5x and take two x's away from it, right? 5 times something minus 2 times something is 3 times the something. Negative 6y plus 2y would be negative 6 of the other thing plus 2 of the other thing. Gives me negative 4 of the other thing. And then our constant of 1. So we can see how we can perform the math here. I can take an x away from another x. I cannot take a y away from an x because we don't know what those are, but we know that they are different. Second example here, 3x squared minus 5x plus 4x minus x squared. I like to put the highest degrees on the left. So the highest degrees that I see are squared. So I have a 3x squared and I have a negative x squared. Put those together and I'm just arranging it so that now I have negative 5x plus 4x, so it's just easier for me to see our like terms. I can go ahead and collect like terms. 3x squared minus x squared gives me 2x squared. Negative 5x plus 4x simply gives me negative x. And then we have a bigger one here with all different types of terms and degrees and variables. So I'm going to quickly go through and identify which variables and degrees are like and group them together. So I have xy, 5xy, I have a negative 2xy, and I have a positive 1xy. So I'm going to group those over here. 6x squared plus 3x squared. Those are the only x squareds I see, so I'm just going to keep those there. I have a negative 4y. I have a negative 5y. I'm going to collect those there. Anything else? Nope. I have a singular x, and that just kind of stays on the end there. Now I can go ahead and collect my like terms when I've gone ahead and rearranged it. So I have 5xy. I end up getting 5xy minus 2xy plus xy, 4xy, plus 9x squared, right, 6 and 3, minus 9y plus x. So that would be the simplified version of this expression.